Hi, my name is Shahin Bayat, and today I will talk about wireless power transmission, or in short term, WPT. This presentation starts with a brief introduction followed by the history behind wireless power transmission in addition to the driving factors to excel in this technology. The concept of this technology is illustrated through interaction between components of the system. Just like other technologies, WPT has advantages and disadvantages which I will cover in this presentation. Technological developments and applications are also explained in this video. Demand for power increases day by day as different technologies advance in their field. As a result of higher power generation and distribution, transmission losses also increase. Approximately 26% of total transmitted power is lost through cable lines and distribution. In addition, limited natural resources call for an unlimited global power solution. The solution to all these problems must be a highly efficient and low-cost system, safer for the environment. Perhaps eliminating cables could be a solution. Let's find out. Maxwell's equations created the theoretical basis of wireless power transmission as Poynting vector described the radio waves as an energy flow. In the 19th century, Nikola Tesla used these theories to chase his dream of world wireless system. He managed to transfer energy from one coil to another in 1897 and successfully lighted 200 lamps from a 40-kilometer distance, and started working on his massive project, the Tesla Tower. The tower was intended to provide wireless power to the entire world. However, this project was terminated due to financial reasons and technical letdowns. In parallel, William C. Brown developed the theory of microwave power transmission. He built the first rectifying antenna and called it the rectenna. This first rectenna had efficiency of 50% at an output power of 4 Watt DC and 40% at an output power of 7 Watt DC. This figure illustrates the largest microwave power transmitter built in 1975 at the Venus site of the JPL Goldstone facility by Brown and Richard Dickinson's team. This rectenna array was placed 1.6 km away from a parabolic transmitting antenna of 26 meter diameter. The klystron source transmitted microwave power of 450 kW at 2.4 GHz. Now, what is a klystron? A klystron is a specialized linear beam vacuum tube invented in 1937, which is used as an amplifier for high frequencies from UHF radio frequencies up into the microwave range. The system outputted a rectifier DC power of 30 kilowatts DC with 83% rectifying efficiency. In 1968, solar power satellites were introduced, which I will cover in more depth later in this video. And in 1995, NASA engaged with this technology. In 2000s, advancements in microwaves started pushing WPT back into consideration for commercial applications. At this point, energy harvesting became a point of interest. Energy harvesting is a process by which energy is derived, captured, and stored from external sources such as solar power, thermal energy, wind energy, kinetic energy, or broadcast radio waves. So what factors keep the wireless power transmission research alive? As mentioned before, cable losses due to transmission of electrical power are about 26%. To meet the increasing demand of power, generation companies have to output more power, and more power distribution means more losses. The transmission can be costly and at risk of power or cable theft. Solution to these issues must consider clean and renewable energy sources. Before I explain how wireless power transmission works, I need to explain some definitions. First of all, let's remember that a magnetron consists of a vacuum tube that produces microwaves by crossing a stream of electrons with a magnetic field. As discussed earlier, a rectenna is a rectifying antenna. It entails a net of dipoles and diodes function to convert microwave energy to electrical energy. With these definitions, we are ready to move on to the component interaction section. Wireless power transmission must be transmitted at a high level and through radiation. One of the ways to implement this technology is by using a microwave power transmission system. Let's look at the component interactions. In an MPT system, AC power is converted to DC. This DC power is then converted to microwave energy using magnetrons. The microwaves are then captured at the other end using a large rectenna and output DC power. This power can then be converted to AC for usage. There are several advantages to using wireless power transmission. These qualities cover areas such as efficiency, maintenance, power failures, and area of coverage. Usage of wireless power transmission method drastically decreases power losses caused by long wires. Since these transmission losses are almost negligible, the efficiency of this method is radically higher than wire transmission. Removing wires from power transmission systems eliminate the need for large substations, towers, and cables while lowering transmission, distribution, and maintenance costs. Moreover, power theft would not be possible with this method. Short circuits and faults on cables will be avoided, which results in less power failures, safer designs, and more savings on budget. Wireless power transmission can reach out to isolated areas where power transmission lines cannot be implemented or are too dangerous. Since wires are eliminated in wireless power transmission, power generation can be extended on a global scale. There are some drawbacks to using wireless power transmission. These shortcomings cover areas such as capital cost, interference, and public health. Although wireless power transmission is financially efficient over time, it requires a large capital for a concrete implementation. This method has to be done very precisely, and even then, it may interfere with current microwaves used in current communication systems. ITU-R radio regulations has a number of frequency bands designated for industry, science, and medical application. In other words, there is no assigned band for microwave power transmission, and it would have to share the same band with the other applications. Current wireless communication systems have a power density that is few orders below that of MPT. Therefore, system designers have to resolve interference issues between the communication systems and MPT. Generally, people fear the effect of microwave radiation. There are many ongoing research in this field. Some believe exposure to low levels of microwaves could be a potential hazard in the long run. Others claim microwave radiation levels would never exceed the amount while opening the microwave oven door, which is just a bit over emissions generated by cellular phones. The IEEE standard for maximum allowable human contact with microwave radiation varies based on exposure awareness of the affected individual and must be met for implementation of MPT and wireless power transmission systems. These are listed at 2.45 or 5.8 GHz, 81.6 or 100 watt per meter squared over 6 minutes, and 16.3 or 38.7 watts per meter squared over 30 minutes. For controlled environments where the individual is aware and uncontrolled environments where the individual is unaware of exposure. Part of major technical developments in wireless power transmission are solar power satellites. These satellites are placed in the geostationary orbit where power generation is 24/7 as there is no night in this orbit. These satellites are very large and the energy must be beamed to precise points on the ground without causing harm or hazard to aircraft, wildlife, or people. The best way to transmit this energy to ground is by a low-intensity microwave beam. These satellites differ from communication satellites in that the solar power satellite beam involves millions of components working together in harmony instead of a singular transmitter to contribute to one beam. The transmitter of solar power satellites consists of many tiny microwave transmitters. Each of these can only produce the power of a light bulb. These transmitters are coordinated together like an orchestra to create a focus beam. The technical term to describe such phenomenon is retrodirective phased array. If the small transmitted beams become out of sync or all turn on at the same time, the result would be noise, and to avoid such situation, a conductor is needed. This conductor is referred to as the pilot beam sent from ground. The receiving station on the ground shoots the beam up to the satellite, notifying the array where to point the beam and synchronize their transmission. The pilot signal is a reference point for all of the elements of transmitters to synchronize and focus their energy to the same location. This synchronization is done by controlling the timing of each transmitter so that the waves are in phase with one another, causing constructive interference. The resulting beam can be pointed to different spots on the ground without any moving parts in a matter of milliseconds. The beam carries a lot of energy at low intensity because the transmitters are small and over a vast area. The beam is even less intense than the signals used for cellular phones, making it safe for life on ground. This technology has been tested on Earth, and the next step is creating prototypes over low Earth orbit. This satellite continuously passes over the ground, cycling the Earth every hour and a half. The beam stays focused on a series of targets while moving at high speed. Then it's moved up to the geostationary orbit, where the satellite remains fixed over the same spot on the Earth, and the beams are tested to point to different locations on the ground. The efficiency and keeping this very large satellite lightweight are the main challenges of this form of technology. As mentioned earlier, one of the main applications of wireless power transmission is solar power satellites. Other applications include providing power for moving targets such as fuel-free airplanes, electric vehicles, robots, and rockets. Furthermore, wireless power transmission can lead to wireless power sources, wireless sensors, and RF power adaptive rectifying circuit. Another wide use of wireless power transmission is inductive charging used in near fields. Maxwell, Tesla, and Brown contributed greatly to the field of wireless power transmission. It is up to the engineers to develop accurate designs to overcome the demerits and challenges of this technology. Should they be successful, wireless power transmission has the potential to grow over a global scale. Thank you for watching my presentation.